Alright, how's it going everybody? So in this video I'll be talking about an algebraic technique called completing the square. And what I hope to do, I know learning algebraic procedures is not always necessarily the most fun thing in the world, but this one actually has what I think is kind of like an elegant little visual picture kind of underlying the technique. So I'd like to share with you the sort of the intuition and also talk about how this thing is used. So our objectives for today are simply to first be able to find the vertex form of a parabola given its factors. So if you haven't already done the exercises involving vertex form and factored form of quadratic functions, make sure you do those before you start this video. This video is all about vertex form, but also about the relationship between the factors and the vertex form. And the second thing we'll be doing is, if you're not given the factors of a quadratic, you could still find the vertex, but it's a little bit harder, and that's where this technique of completing the square comes in. So completing the square allows us to find the vertex of a quadratic when we maybe don't know what the factors are already. So let's look at some examples to clarify everything here. So this first, just to kind of remind you of the vocabulary and everything, like I look at this red parabola over here. This is a graph of a quadratic function. The roots, or what are called the x-intercepts, or also called the zeros, all mean the same thing, are just these 2 points at 1, 0 and 5, 0. Okay, that's just where the parabola crosses the x-axis. Okay, and the vertex is this point down at the bottom, which is the point that lies sort of right in the middle of the parabola. It's sort of everything to the left of that point looks the same as everything to the right of it. And it's occurring here at the minimum of the parabola. And the real intuition here relating the roots and the vertex is simply that you notice that since the vertex is in the middle and the roots are sort of evenly balanced on either side, then the vertex has to be halfway in between the two roots. So in this picture, the green root to the left is at x equals 1. The purple root to the right is at x equals 5. So the vertex must fall in between 1 and 5 and on the x-axis. And what number is between 1 and 5? Well, that's 3, right? And so my vertex had to be at x equals 3. So just keeping in mind that relationship as we go on here. Because if we look, if you look here algebraically, same thing, okay? The factored form, now I've actually given you the function which made this picture, and I've given it to you here in factored form. This shows the information of the roots, right? So it tells me that there's a root at x equals 1, that's this first factor, and there's a root at x equals 5, that's the second factor. So factored form, it's easy, it's conveying the information of the quadratic in terms of those two roots. Vertex form, on the other hand, is conveying the information of the parabola algebraically in terms of where the vertex is, right? So in this case, this x minus 3 tells me that the vertex has to be at 3, and then this minus 4 tells me that the y-coordinate has to be at minus 4. So just, this should be reviewed from the vertex and factored form assignments, but remembering that you can read off the algebra certain distinguished features of the actual graph of what it looks like when you graph it. Okay. All right, so let's do one more example here. I've asked you to find the vertex given the function, although I've given you a picture here which tells you what the vertex is. I guess what I'm saying here is if you can graph something, just graph it and figure out where the vertex is. But let's say you didn't graph, okay? Instead, what you could do is kind of use what we just talked about and first find where the roots are by factoring, okay? So notice that I can factor this thing by just saying, look, x squared plus 6x, each of those terms have an x in them, so I can factor out that x. Notice this is the distributive property in reverse, right? The x times the x gives me an x squared. The x times the 6 gives me a 6x. So to factor this thing from y equals x squared plus 6x, I can pull out an x, and that gives me x times x plus 6. Well, now it's in factored form. There's this first factor corresponds to the root at 0, which I can see up there. And the second factor gives me the root at minus 6, which I can see here. Okay. Now, since you know where the roots are, you know that the vertex has to be halfway in between, and halfway in between 0 and minus 6 is negative 3. To figure out what that y-coordinate is, you know it's at x equals minus 3. To figure out the y-coordinate, just simply plug in to the function. You have the function, just plug in. And when you do that, you'll get negative 9 out. Okay, so this is just an example where if you can factor your function, you can figure out the roots, and from the roots you can figure out the vertex. Okay. However, and here's the problem, what do you do when you can't find the factors, or they're not given to you, or there just are none? So in this picture over here, there are no x-intercepts. I can't just say find the roots and look halfway in between, because there aren't any x-intercepts to find, right? But it still has a vertex, and I still should be able to figure out where that vertex is. And so this is the motivating question for this technique of completing the square. So we will use completing the square to go from this algebraic form here to figure out what the vertex is and what the vertex form of the quadratic is. Okay. All right, so let's look at this thing. Let's do a simple example. This example you could do without completing the square. It's probably a lot easier to just factor and figure out where the roots are like we did a minute ago. But let's do a simple example to start. Let's say I have the quadratic function y equals x squared plus 6x, and I want to find where the vertex of this thing is. So here I'm going to complete the square. There better be a square involved. Okay, and in fact there is. And here's my picture of the square. What I'm going to do is I'm going to try to just play with these little variables and pretend they're little tiles. This should remind you a little bit of the pictures we drew when we were factoring quadratics using the area model of multiplication. Okay, so what I'm going to do here is I'm going to try to get this x squared plus 6x to show up as the area of this big square, the square that we're talking about here. So notice that there are these two blue pieces, and I want them to capture the 6x part. Okay, the x squared part is already captured here. It's by doing an x by x box that has area x squared, and I'd like to get these other two pieces to add together to be 6x. Well, how do I do that? Well, I take half of that, and that gives me 3. Half here, 3. Why is that? Because what's the dimensions of this box? It's 3 by x, so its area is 3 times x. And this one, it's 3 units up and x units across. Its area is 3 times x. So you see now I have a slightly more complete picture where I have the x squared, I have 3x here and 3x here, and of course 3x plus 3x gives me a total of 6x. Now what's left to do is to figure out, this is the completing part, what goes in this last square, and then we'll put it all together. Okay, it's just like playing with little blocks or something. That's what this whole scary sounding technique is, just like moving little tiles around like when you're in elementary school. Okay, so of course, how do I fill in this red piece? It's 3 by 3, so its area is 9. And then the main observation here is just to notice, look at this big square we built. It's x plus 3 units across. That's right here, x plus 3 across. And it's x plus 3 units high, right? So it's x plus 3 by x plus 3. So the area is just x plus 3 times x plus 3, or x plus 3 squared. So the whole square has area x plus 3 squared. And now remember, we started with just the x squared plus 6x, so it's like this red piece was kind of extra. So all I have to do now is subtract off the red piece from the total area, and let's look at that. Okay, so let's digest everything here on this slide. We started with y equals x squared plus 6x. I see that in these 3 pieces of the square. There's my x squared plus 6x. The square, the total area of the whole square is x plus 3 quantity squared, but that gives you too much. I have to take off this piece here, this 9. So this gives me a subtract 9. And you notice when I write it like this x plus 3 quantity squared is the whole area of the big square. This subtracting 9 is taking away that piece on the top right. That makes these two things equal, because it's left equal with x squared plus 6x. That's all that's left over. And what did that do for me? Well, guess what? This thing down here is the vertex form, right? Its vertex is at, I can read off the vertex now. It's at x equals -3, y equals -9. So this, if I graphed this quadratic function and looked at the parabola, I would know where its vertex is. It's at -3, -9. And just taking a moment to being able to read that off of this picture, right? 2 different ways to represent the same thing. They just convey different information. This one on the bottom conveys the information about the vertex. Okay, this one on the top conveys some different information about the quadratic, really how fast it's growing. All right, so let's do a couple more examples, but you'll see it's like it's pretty easy to get into the swing of things here. Okay, so x squared plus 10x, another one like a lot like we did. I want to build out this square that captures the x squared and the 10x piece, so I know it has to have an x by x to give me the x squared. How about the 10x? Well, I'm going to get it from each of these blue pieces, so it better be 5 and 5, because now I have a 5x and a 5x. So all together, of the pieces we filled in, I have x squared plus 5x, or x squared plus 10x. Now what am I going to do to complete my square? Again, it's called complete the square because you are completing that missing piece we have. Well, what's its area? It's 5 times 5, which is 25. So then to put everything together in vertex form, to get the vertex form, what am I going to do? It's going to be y equals, what's the area of the whole square? Well, that's x plus 5 quantity squared. That gives me the whole square because it's x plus 5 units across and x plus 5 units up and down. So its area of the big square is x plus 5 quantity squared. What do I have to subtract off? I have to kill off this last piece to leave me with just what I wanted, x squared plus 10x. And notice you can read off the vertex now. The vertex is at x equals minus 5 and y equals minus 25. Okay, so all these kind of work the same way. Here I've done an example where you get some fractions, but that's okay, nothing really changes. You start with x squared plus 7x and you want to get its vertex form down here. Okay, so what do? You take half of 7, which is 7 over 2 and 7 over 2. Okay, those three pieces give me the x squared plus 7x piece. And what's left over, what's the extra piece, the red piece, is 7 over 2 times 7 over 2, which is 7 times 7 is 49. 2 times 2 is 4. So we divide them. And again, here's the area of the square, this square over here. It's x plus 7 halves times x plus 7 halves. And we take away the red piece. And this leaves me with the vertex form. Okay, so you should, at this point, basically be able to see the steps. If you want some steps for doing this procedure, it's take half of that middle term, in this case the 12x, take half of it, that gives me 6. Then I multiply 6 by itself to give me 36, and I just plop these things into the vertex form down here. Or if you like to go through the picture, which is really what I like to do because it helps me keep everything straight, if it has to give you 12x, then you should make it half of that, which is 6 and 6. 6x and 6x adds to 12x. This remaining piece has size 36, so I subtract off the 36. Okay. All right, so let's do one more example, and this is kind of really the motivating thing. An example where there are no factors. So like this guy doesn't have any x-intercepts. Okay. But we can still find the vertex by completing the square. And how are you going to do it? Well, here's that function, y equals x squared minus 3x. You're literally just going to do the same thing you did 2 seconds ago, except you're just going to ignore this plus 4 for now. So we're just going to work with the x squared minus 3x part. So what did we do? Let's go through the steps again. First, you take half of that term there, that minus 3. So this is minus 3 over 2, minus 3 over 2. Okay, and that gives me negative 3 halves times x in this piece and negative 3 halves times x in this piece. What's the missing, the part that you need to quote unquote complete? That's what goes up here, which is 9 divided by 4. Negative 3 halves times negative 3 halves is 9 divided by 4. Okay, and now all you have to do is to get my vertex form. Let's see, did I make a slide? Oh, I already made this on the next slide. Here's what we just talked about. Negative 3 halves x, negative 3 halves x. And you can see the algebra here. Here's my vertex form. The dimensions of the square are x minus 3 halves by x minus 3 halves. So that's x minus 3 halves quantity squared. Okay, then you have to subtract the red part, subtract 9 over 4. And remember, we just have to have this little plus 4 tag along. So you complete the square just on the part to the left, this part, and then you just let this plus 4 tag along because you can add 4 and negative 9 quarters, and that'll get you 1.75. So notice that now I have y equals quantity x minus 3 halves squared plus 1.75. So my vertex here is at x equals 3 halves, y, oops, I don't know why I did that, 3 halves, and y equals 1.75. Okay. So even when it's something that where you can't find the factors easily, you can still do this procedure. Okay, so that'll wrap it up for this video. What the success criterion or a summary here is, the vertex is the point in the middle of the parabola. The factors tell you where the x-intercepts are, so you know that if you have it in factored form, you can look halfway in between to find that vertex and get the thing in vertex form. Okay. Algebraically, you should be able, as I just said, you should be able to go from factored form to vertex form. And then lastly, you should be able to complete the square to get the vertex form of a quadratic, even without the factors. And that's just following those steps we reviewed a minute ago. All right, so thanks for listening and have a good one.